In this video, I'm going to talk about per unit normalization. Per unit normalization is a circuit solving technique that can make systems involving lots of transformers, typically those seen in power generation circuits, a lot easier to solve. So to show how this works, we're going to start with an example problem. So let's say that we have an AC voltage source that supplies V1 volts. This is going to be connected to a resistor. It's also going to be connected to a transformer coil. And then the other side of the transformer coil is over here, and this has another resistor across it. We'll call this resistor 1, we'll call this R2. The turns ratio between the two sides of the transformer is N1 on the primary and N2 on the secondary. So if we wanted to solve for the total power that was being supplied by V1, or the voltage source, which we will call PS, how would we go about solving for this? Well, first, we need to find what the voltage is across R2, and we'll call this V2. So, using the transformer ratio equation, we know that V2 is going to be equal to the ratio of turns on the secondary side to the number of turns on the primary side times V1. Now that we know what the voltages are across both of the resistors, because R1 just has V1 volts across it, we can write a pretty simple expression for the total power. We can write that the power supplied is going to be equal to the magnitude of V1 squared over R1 plus the magnitude of V2 squared over R2. And then, if we substitute this equation in for V2, we can write V1 squared over R1 plus V1 squared over R1 times the turn ratio squared. So this was pretty simple and it wasn't too bad to solve. But you'll notice that we only had one transformer in this system. If we had several transformers, like 2, 3, 4, even 5 transformers in the system, that's going to be even more turns ratios that we need to keep track of. And this method is very quickly going to become error prone. So what we want is a way to solve this circuit without having to care about all the transformers that are in it. And this is what per unit normalization will allow us to do. So to start, we're going to define a couple of per unit values. And you'll sometimes see per unit abbreviated as PU. So the first value that is typically defined whenever we're working with the system in per unit is what's called the power base, and we're going to call this S base. Now, this is a value that you can pick anything for it to be. However, on tests and homeworks, this will typically be given to you. That way your other values match up with the solution. For typical power systems, a good value is 100 megavolt amps. So next, we need to define what's called base voltages. I'm going to need two of them. We're going to define one as V base 1, and the other one's going to be called V base 2. So if you look on our circuit, you can kind of see that we have two different regions. We have one side on the primary side, which we will call the low voltage side, and then we have N2, which can be the high voltage side. Each of these regions is going to have a base voltage associated with them, and you're going to define this based on the nominal voltages. So we'll start with defining V base 1, and we're going to use the nominal voltage, whatever it would be in your case. But then, for V base 2, we want to keep the relationship between V base 2 and V base 1 the same as the turns ratio. So what we're going to write is that V base 1 over V base 2 needs to equal our turns ratio, so N1 over N2. And again, we're not actually picking values for these yet, we're just doing it all symbolically. So then, the way that per unit works is, let's say that we want to express V1 in a per unit quantity. The way you're going to express circuit parameters is going to be the circuit parameter, so we'll say in this case V1, is going to equal the base voltage, so V base 1, times some per unit value. So all this per unit value is basically a scalar multiplied by the base value that actually gives you the voltage, V1. So if we define V base 1 to be equal to V1, because that is the nominal voltage for this region of the circuit, you can see that VPU1 would just be equal to 1. It is saying that V1 is equal to just the base voltage times 1. For V2, we would write similarly, V2 equals V base 2 times V per unit 2. So before we can actually solve the circuit using per unit values, we need to define a couple of extra relationships. So to start off, we need to define an impedance base. This is going to be similar to the voltage base, but the relationship's a little bit different. So to define an impedance base, we're going to write that the impedance base is going to be equal to the voltage base squared over the power base. Similarly, for region 2 of the circuit, we can write that the base impedance in this region is going to be equal to the V base 2 squared over S base. We can also write relationships for the current base, and we can say that the base current in region 1 is just equal to the power base for the whole system divided by the voltage base in that region. Same thing for region 2 of the circuit, where I2 base is equal to the power base over the voltage base in that region. So again, similarly to how we defined voltages in terms of their base voltage times some scalar, the per unit value, we can write that R1 would just be equal to the base impedance in that region times some per unit impedance. We can do the same thing for Z2. Okay, I just said that R1 equals Z base 1 times Z per unit 1. This is technically incorrect, because most of the time when we use R as a symbol to denote impedance, it's talking about a load that has a purely real impedance value. So anytime you see me write R1 equals Z base 1 times Z per unit 1, this should really be that Z1 equals Z base 1 times Z per unit 1. Just wanted to clear that up. So now, using these relationships, we can start to solve this circuit using per unit values. So first, let's go back to one of the basic relationships in this circuit. So we know that in our circuit, we wrote that V2 was equal to the turns ratio times V1. But now, let's write this using our per unit values. We can write V2 as V per unit 2 times some base voltage. We can write the turns ratio, N2 over N1, times V1 expressed in per unit form, so V per unit 1 times V base 1. And right now, this might just seem like it's making this problem more complex than it needs to be, but I'll show you why this is useful. So, if we divide both sides by V base 1, on this side, this is going to cancel out with this V base 1 here. But over here, let's look at this expression that we have of V base 2 over V base 1. If you remember earlier, we defined the relationship between V base 2 and V base 1 to where the ratio between V base 1 and V base 2 needs to equal N1 over N2. So now you notice we have V base 2 over V base 1. So we can substitute this for N2 over N1. And now you'll notice we have an N2 over N1 on both sides, and they're going to cancel. This whole entire expression simplifies to V per unit 2 is equal to V per unit 1. This is saying that the voltage in both regions of our circuit, when expressed in per unit values, are identical to each other. So even though these voltages may vary wildly in what they actually are, like this side could be 100 volts, this could be 10,000 volts, their per unit values are going to be the same. So let's write down that expression that we derived for power earlier. We know that the total power supplied by our source was equal to V1 squared over R1 plus V2 squared over R2. But now let's substitute in the per unit values. What we're going to get here is V per unit 1 squared times V base 1 squared. This is going to be divided by R per unit 1 times Z base in region 1. This is going to be added to V per unit 2 squared V base 2 squared. All of this over R per unit 2 times Z base. So I want you to remember that this entire expression here is equivalent to this one here. We have just rewritten it using per unit values. That's why it may look a little confusing. So, as we did before with the voltage, let's look and see if there's any simplifications that we can make from this. If you notice, we have V base 1 squared over Z base 1. And we defined this earlier to be equal to the power base. On this side, we again have the base voltage squared over Z base. This is also equivalent to S base. So defining one more relationship here before we fully simplify this circuit, let's think about how we would write power in per unit notation. So PS would just be equal to some power per unit value times our S base. What you'll notice here is that we can rewrite this side as S base times V per unit 1 squared over R per unit 1 plus V per unit 2 squared over R per unit 2. So if we rearrange the circuit, we can see, rearrange this equation, we get PS over S base equals R, or power per unit. You can see here we're going to divide both sides by S base, and we're going to end up with P, power per unit, is equal to this expression here. So we have V per unit 1 squared over R per unit 1 plus V per unit 2 squared over R per unit 2. Okay, so now let's look at this equation and think about it for a bit. So remember, our original circuit started out as we had some power supply that delivered power to a resistor and into a transformer, which was connected to the other side of the transformer with a resistor. This was our circuit. Now our expression for power is equal to some per unit value squared over the resistance value plus another per unit value squared over another resistance. But now the key thing to remember is that we derived earlier that V per unit 2 is actually equal to V per unit 1. What this means is that we can make some further simplifications to our power expression. We can write that this is equal to V per unit 1 squared over R per unit 1 plus another V per unit 1 squared over R per unit 2. And this should be the magnitude of this here. It's like this. So what we have here is our total power is equal to some voltage across two resistors. Now what kind of circuit would give us this equation for power? It would just be our voltage source that provides V per unit 1 over two resistors in parallel, where this is R per unit 1, and this is R per unit 2. So now we have modeled this circuit in such a way that we do not have a transformer in it. Now there are still different regions in this circuit, as this is region 2, where we have our higher voltage, and this is region 1. But in our circuit model, we no longer have to explicitly model a transformer. And this is why per unit normalization is so helpful. it allows us to take transformers out of the circuit and to solve it using regular circuit analysis techniques. So I'm going to stop here in this video, and in the next video I'll work through an example problem and also cover something called base conversions.